is now the appointed hour. Time to start talking. All right, so here is where we left off. Does anybody have any questions about anything before we start? I was a little concerned about something. It seems like a lot of people haven't started doing their homework yet. Have you guys got access to the book and whatnot? So, good. All right, well, let me know if there's any issues. But okay, and I know we jumped topics quite a bit in the beginning. I do apologize for that. I mean, it's great for me with ADD, but for you guys, normal people, it can be kind of cumbersome. Another reason why people don't like chemistry, because there's so many different topics all given to you at once. And they're all interrelated, of course. And so right now we're talking about solubility rules. So solubility means you can dissolve it in water. So salt, sodium chloride salt, is very soluble in water. It is 3 to 1, 3 parts water, 1 part salt. So you can fit 25 grams of salt in 75 grams of water. So it's a lot of salt. If you ever made brine before, it takes a lot of salt, a long time to dissolve all that salt into water. So that's soluble. Insoluble is, we cover this in the lab if you're taking the chem lab. Calcium carbonate is insoluble. So coral, limestone, marble is calcium carbonate. You put it in water, it doesn't dissolve. So these are the rules that allow things to be soluble or insoluble. So in the last class, I had a hard time seeing some of these things. But the first one are the alkali metals and ammonium. So lithium, sodium, potassium, also rubidium, cesium. These are always soluble, no exceptions. And the negative anions, acetate and nitrate, those are both always soluble. And then now we have the halides, chlorine, bromine, iodine. And these are usually soluble unless it's paired with silver, mercury, or lead. So those are insoluble, meaning they won't dissolve, but the rest of them are soluble. And then sulfate tends to be soluble, with the exception of the alkaline earth, silver, the alkaline earth and silver. I don't know why the book put calcium last. Oh, and lead too, lead sulfate, insoluble. So those are the general solubility things. Then we have hydroxides. So these tend to be insoluble, and hydroxides and sulfides are insoluble unless there's alkalis or ammoniums, because they're always soluble. And sulfide with the alkaline earths tend to be soluble, and hydroxides with the alkaline earths are slightly soluble. I personally wouldn't call them slightly soluble. They're not really that soluble at all. Like lime water, calcium hydroxide, you can put it in water, you get lime water, you can drink it. So if you drink sodium hydroxide lye, you're going to go to the hospital or you're going to die if you drink that stuff. But calcium hydroxide you can drink, and it can even soothe your stomach. Carbonates and phosphates, those are insoluble with the exception of alkalis and ammoniums. So let's apply that. Which of these compounds are soluble or insoluble? So the way, look at this, so here lead chloride, start with lead chloride. And so look at the chlorides. Chlorides tend to be soluble, so chlorine is right here, tends to be soluble except for lead. So because of that, because of the except for lead, this is going to be insoluble. So I for insoluble. So does everybody understand the logic that I'm going through? Okay. So copper chloride, chlorines tend to be soluble. Copper is not a exception, so it's soluble. Calcium nitrates, all nitrates are soluble. Barium sulfate, here's sulfate. It tends to be soluble, but barium is an exception. It's insoluble. So does that make sense? How is this going? Okay, so just using the chart. And they like to use these questions on things like the MCAT because they're very logic-based questions. So next thing we'll talk about are precipitation reactions. We are going to do a lab on this. We're not there yet. But you basically take two solutions and you mix them together, and you can form a new compound that's no longer soluble in water, and it falls to the bottom. That's called a precipitate. So sometimes you mix solutions. And you can get stuff that goes to the top. Those are called supplicants, actually. But we're not going to deal with them in this class. If you're wondering, sometimes things float, but they usually don't. So precipitates, they fall to the bottom. And so when you look at these equations, and I saw my teacher evaluations complaint that I bring up heteronormality too much. So I'm just using this to illustrate a point. So pardon the heteronormality in this equation. But what I'm implying is, so we have positive potassium. The positive ions are always first. The last class asked me which one's the positive ion. Positive ions are always first, negative or second. So we have positive potassium with negative carbonate dissolved in water, combining with positive nickel and negative chloride. And the positive ions will not mix because they repel. So the positive ions do not like other positive ions because of Coulomb book repulsion. The negative and the negative also do not attract because of repulsion, so only the positive and negative. So in this way, you would have this positive ion would mix with this negative ion here, like that. And likewise, this negative ion would mix with this positive ion like that. Sometimes this is referred to as a partner exchange reaction. And the question is one of these insoluble? If one of these is insoluble, then a precipitate will form. If both are soluble, then no reaction happens. So with this first one, so if you see here, potassium carbonate reacting with nickel chloride, this is going to form KCl, so this one and that one, and then plus nickel carbonate. This is 2 there if you want to balance, there's a 2 there. Okay, so the question is potassium chloride or nickel carbonate insoluble? So let's go back up here. So we're going to KCl and nickel carbonate. So all potassiums are soluble. That's easy. That one's done. Carbonate are insoluble with the exception of, so you can't, can you guys read that? It seems like, okay. So it's soluble with the exception of the alkalis and ammonium. So nickel is not one of the exceptions, therefore it's insoluble. So since this is insoluble, it will in fact form a solid and drop out of solution. Oh, and the other thing is some of the old textbooks would have an arrow, instead of a solid, they have an arrow down, and they also have an arrow up for gas. So arrow down for precipitate, arrow up for gas. So does this make sense, everyone? Questions here? Okay. Next one. So sodium nitrate and lithium sulfate. What happens here? Well, it's going to form lithium nitrate and sodium sulfate. But if you look at the chart up here, all alkalis are soluble. And it's just, these are all soluble. So what happens here is no reaction. And that RXN, seeing this RXN, then RXN means reaction. So this means that you mix these two together, absolutely nothing happens. So it's a boring thing to do. All right, questions with this? Okay. So put copper chloride and lead nitrate. Is there a precipitate? So let me go back up here. Copper chloride Should have copied this here. I can copy it. How many think A, we're forming copper nitrate? Solid, precipitating out. How many think B, lead chloride? How many think C, dichlorine nitrate? How many think D, no reaction? Okay. We got some confusion, so I will come around. So go ahead and break up in your groups. These are soluble. Is anybody stuck? I guess a lot of people are stuck. I guess. Okay. What are you going to form? So first of all, you're going to form copper nitrate. And, well, this is going to be aqueous. And the other thing you can form is lead chloride. I even put it as, it's not copper nitrate. All nitrates are soluble. Are you guys having a hard time seeing the chart? Is that part of the problem? No, okay. All nitrates are soluble, so you know that copper nitrate is soluble. What about lead chloride? Is it soluble or insoluble? So chlorines tend to be soluble, but lead is an exception. So because of that, you're going to form lead chloride precipitate. Is that making sense? Okay. All right then. We got to go to the next. Questions with that? All right, now we're going to talk about the different type of equations. So this equation, as written, is a molecular equation. We have lead nitrate aqueous plus 2 parts potassium chloride aqueous makes lead chloride solid and 2 potassium nitrates aqueous. And so in my mind, when I see this, I imagine myself going in the chemistry stock room, grabbing a plastic container of lead nitrate, taking off the top, putting a scoopula in, taking the solid stuff, it's a white kind of crystal-y stuff. You put it into a beaker, and I fill that with water, let it dissolve. Potassium chloride, also white solid. I take that out of a different plastic container, I put that into a beaker, and then I pour them together, right? So I have these 2 reactants in each individual beakers, pour them together, all together, and then this lead chloride, it's a yellow sort of color. Yellow stuff comes to the bottom. Now, this right there is a molecular equation. What lead and nitrate aqueous is actually lead ions. We can see this. We have the lead ion and the nitrate anion. Then we have 2 potassiums and 2 chlorines there. All of these aqueous. And what's formed? That's formed there. And then potassium nitrate is then on both sides there. So this bottom one here is known as the complete ionic equation. So all of the ions are accounted for. So this is the person that talks, it's just me when you ask me a question in the lecture. I talk too much, right? I tell you the whole story, the backstory, and then some other things. That's one of my issues. I give dollar answers to nickel questions. So this is like me talking. Now, if you've ever played a sport, or if you've ever, most of us observed a sport, so say you go watch a baseball game, you're sitting in the stands, you're a spectator, you're observing the game. So it means that if you're watching a baseball game, you're not the one up the bat, you're not the one throwing the ball, you're not the one catching the ball. You are just there watching. So if you look at nitrate and potassium, they are on both sides of the equation. That's kind of cool how the blue looks different in a different shadow. Huh. Anyways, they're on different sides of the equation, and therefore, they're on the same side of the equation, and they don't actively participate in the chemical reaction. So because of that, they're spectators. Just like you at a baseball game observing, you are not partaking in the game. So what you can do is you can get rid of the spectator ions and then have what's called the net ionic equation. So this right here is the net ionic equation. So do you guys ever use Cliff's Notes or Spark Notes for classes? I used to use those all the time, right? So you go to Grapes of Wrath. It says, the Jodes left Oklahoma, they came to California, and they're still poor, and it ends with a curious smile. That's like the Cliff's Notes. That's Grapes of Wrath right there, right? So you don't have to read the book. I can look at the Cliff's Notes. So this is the Cliff's Notes to that reaction. Lead and chlorine get together and form a solid. End of story. So don't care about the preacher. They don't care about picking peaches. They don't care about Grandma Jode dying on the way, right? So that's just not included. Jodes went to California and they're still poor. This is the really short and quick, easy version. What happens? So, questions with the different types of equations? All right, so we're talking about acids and bases next. Again, changing topics yet again. Acids and base. An acid, the simplest way to describe an acid is that if you throw acid in water, it forms hydronium ion, H3O+. If you throw a base in water, it forms hydroxide anion. We will go into this much more in depth later. Chapter 15 in the book, and 162, Chemistry 162, we will talk about acids and bases in much, much greater detail. But we're just going to keep it very simple right now. And some acids, most acids are monoprotic, meaning one proton, one H that it gives off. Some acids and bases are polyprotic, like sulfuric acid, so H2SO4. So that means that H2SO4 has 2 parts acid in it, so 2 moles of acid are in 1 mole of sulfuric. So here are some common acids and bases. So real briefly, hydrochloric, that's our stomach acids. So the acid, we have acid in our stomach, and it's in fact hydrochloric acid. And we can have a pretty low pH in our stomach. So I haven't eaten in a while, so my stomach pH is probably on the order of 5. Anything less than question? Oh, jeez. Why does this do that? I thought I quit Skype. Nah. Sorry about that. So stomach acid, hydrochloric acid. Hydrobromic hydrochloric is not used very frequently outside a chemistry lab, to be quite honest with you. I don't know why it's listed as a common acid. Nitric acid, that's pretty common. Used to make explosives. We talked about that before. Toluene, 3 parts nitric acid to 1 part toluene gives you trinitrotoluene. So sulfuric acid, this is in the United States, we make a bunch of sulfuric acid. And so the number one thing that we make as far as chemicals is transportation fuels. Not a big surprise. Can anyone guess what the number 2 thing is that we make in huge quantities?
Acid.
What's that?
That acid?
Yeah, that acid, yes. But what do we use it for? What's it? Crops. Fertilizer. Yep. Fertilizers are number 2 as far as our things that we make as human beings. So make lots of fuel, and then secondly, make lots of fertilizer. So sulfuric acid used to make, among other things, ammonium sulfate, which is a very common fertilizer. Perchloric acid, we use that to make explosives. We used to use it to make cheap fireworks. Well, used to. Many of the fireworks coming out of China are from perchlorates. and they're the smoky ones. So maybe you've noticed this. The firework displays, at least, well, we have them more frequently on Oahu. Do they have firework displays here on Maui? I haven't seen any yet. Okay. They, oh, okay. That's when they changed the laws. Yeah. Yeah. They changed the laws here in Hawaii that you cannot use perchlorate fireworks. You have to use nitrate fireworks. So the reason is they burn cleanly, like because they're really smoky. Like if you go to the firework displays, there's lots of smoke everywhere. That's from the perchlorates. The nitrates tend to have less smoke, and they're also more expensive. So I guess the special occasion. Yeah, I was wondering about. There's no fireworks here. Well, what about New Year's Eve? Really? Man, Oahu, everyone blows that thing up, and like it's try to take a nap after noon, you can't because there's an explosion every 20 minutes. All right, well, yeah, huh. All right, well, acetic acid, that's what's in vinegar, so the red one down there. Hydrofluoric acid. Now this stuff scares me. So hydrofluoric acid, if you get it on your skin, it's a surface anesthetic. And surface anesthetic, which means you can't feel it. And it's also hydrofluoric acid seeks out calcium. So, and I know two people this happened to them. They got hydrofluoric acid on their back of their hands, and they didn't feel anything, but they heard a sound, and they saw white foam coming from the back of their hands, and it was the hydrofluoric acid eating their bones. And since it's surface anesthetic, you can't feel it. The problem is that it's dissolving your bones. If a bone chip gets in your bloodstream, it can cause a heart attack or a stroke. So the treatment for it is to rub calcium glutamate, a lotion on. You rinse it off first with water, but then you have to neutralize it with lotion. So my sister, someone who worked with my sister, well, I have three sisters, and one of my sisters is an environmental engineer. She was at a metallurgy plant, and her partner, she got splashed with effluent from a stream that was on there, like inside the plant, and it could have had hydrofluoric acid in it. So what they did to her was they stripped her down and threw her in a shower, and then they put her in a body bag and zipped her up and took her to the hospital to check her out. So she was fine, but that was one of those, like, how was your day, honey? So you don't mess around with hydrofluoric acid. And it dissolves glass. So if you've ever seen glass that has like white frosted things on it, that's from hydrofluoric acid. So nasty stuff. It scares me. And common base here is sodium hydroxide. That's also known as lye, L-Y-E, lye. So if you hear this, oh, it's got lye in it, that's sodium hydroxide. Sometimes also called caustic. And lithium hydroxide, potassium hydroxide, not used too much. Calcium hydroxide, a little bit, used to make cement. So cement, if you argue, you could use in cement. Calcium oxide is a lime, and if you mix lime with water, you form lime water, which is calcium hydroxide. So, and another fun fact, calcium hydroxide lime, if you heat it up, it glows. So you ever heard in the rap song people being like addicted to the limelight? So that's how the old-fashioned spotlights, like back in 1800s, you would take lime and you heat it up, it glows, and you put some mirrors behind it. In a dark room, that would be a spotlight. So you're addicted to the limelight. Lime actually can be used to have a light. And ammonia, barium hydroxide, not used very commonly. I don't know why it's common base. Ammonia, very, very common base. We talk about that with fertilizer. Okay. So let's talk about writing acid-base reactions. And acid-base reactions, they're pretty easy. For the net ionic equation, the net ionic equation is just H plus OH minus makes water. So those are nice, but let me back up a bit. So we have an acid and a base to form water and a salt. So acids. So we have chemical sensors on our tongues. That's taste is a chemical sense. So we have 5 senses of taste. We have acid, base, sweet, salty, and savory, the umami. So our acid flavor is our sour flavor. Our base flavor is our bitter flavor. So acids taste sour. So I told you hydrochloric acid is an acid, and I'm sure everyone in his or her life has thrown up, and it tastes really sour. So stomach acid tastes really, really sour. Vinegar tastes really, really sour. So, and humans are programmed to not like sour things. We're also programmed to not like bitter things. So what's bitter? Have you ever had like NyQuil or Robitussin, but the cheap stuff from Walmart isn't that full of sugar and stuff? You drink that stuff, you're like, ugh! That's bitter. That is the bitter flavor. And the reason why humans hate it is because things that are bitter tend to be toxic. So, and there's a whole bunch of things that we still consume things that are toxic. Caffeine. Caffeine is extremely toxic. And a really hefty cup of coffee has 100 milligrams. So 100, like 0.1 grams. That's not a lot of caffeine. So very, very little. And it takes a lot of coffee to get a lethal dose. So you basically would burst from water poisoning. So, but caffeine, if you get by powdered caffeine, start eating scoops of powdered caffeine, yes, you're going to die. So, because it's very toxic. And not only that, I'm sure it would taste terrible because it would be very bitter. Okay, but I mentioned that acids taste sour, bases taste bitter. You can make sodium chloride salt by mixing hydrochloric acid and sodium hydroxide. So hydrochloric acid, we already know it's our stomach acid, tastes sour. Sodium hydroxide, I've never tasted it, don't taste it. I'm sure it tastes bitter. So it'll probably also give you sores in your mouth if you taste it as well, because it's going to be really, really bad. So as before it dissolves your mouth, it'll taste really bitter. But what about sodium chloride salt? Does it taste sour? Does it taste bitter? No, it's not an acid or a base. It's a salt. It's something new. It no longer has the chemical properties. So there's 2 definitions for salt in chemistry class. The first definition is a metal and a nonmetal that are not, that the nonmetal is not a hydroxide or an oxide. So that's the first definition, metal plus nonmetal. The nonmetal is not a hydroxide or an oxide. Second definition is the result of an acid-base neutralization reaction. So acid-base reacts to form a salt. The salt no longer has the properties of the acid or the base, as proven by our own sense of taste, if you will. Okay, so this equation here, so we're going to balance it. So another hint, when you balance some things, I tend to look at these hydroxides and I look at them as one unit. So I look at this H reacting with this OH to form water. And I don't look at it as hydrogens and oxygens individually. So, and since there's 2 hydroxides here, there's going to be 2 waters there, and then there's going to be another 2 hydrogens there. So you can balance it that way using those units. And then the barium and the iodine is already balanced there. So one barium here, 2 iodines, 2 times 1 there for the iodine there. So it's all balanced. So, and then the molecular equation. Okay, there's the molecular. Oh, it's already balanced right there. Balanced molecular equation, and then the total ionic equation is just since the barium and iodine ions are already in solution, you can get rid of the barium and iodine, and the net ionic is just H plus acid plus OH minus hydroxide makes water, and so that's all acid-base reactions is just a fancy way of saying I'm making water. Okay, questions with this so far? All right, titration, and so a titration is an old, we still use it today, and you'll do titrations in chem lab, but I feel a little conflicted sometimes because no one really does titrations anymore. It's very few people do titrations, and most of the time, we do titrations, but they're done by robots. Okay, so humans, there are very few instances where humans do titrations now in this day. So what I mean is, if you go to the hospital and you get blood work done, you get your blood drawn, and what do? They put it into a machine, and the machine has the blood comes in, and they have little robotic arms. They put blood into some things, and they do a series of chemical tests on it, and then the results spit out of a computer. So the only thing the person does, we have a person that draws your blood, and then we have a person that puts the blood in the vial and sticks it in the machine. Or it's already in the vial, I guess. Actually, I've never seen the medical ones. There's got to be some input. It's probably a human that does that. But all the rest of the stuff is done by robots, right? So, and it's a titration. A titration is a way of figuring out how much of stuff is in something. So, and you have an unknown, and you have a known. You have something that you know the concentration is, and you compare it to your unknown. And like I said, we'll do this in Chem Lab. Two ways you can do an acid-base titration. One way is to use a pH probe, and when the pH probe goes to 7, that's the neutral, then it's done. So pH 7 is neutral, above 7 is alkaline base, below 7 is acid. The other way you can do it is using an indicator. So this one here, we're taking hydrochloric acid and we're adding sodium hydroxide to it. The solution is going to be one drop after it's going to turn alkaline. You can use something like phenolphthalein. It turns it pink. So when it turns pink, you know you're done. So this problem here, we have 10 milliliters of an unknown hydrochloric acid solution. But it takes 12.54 milliliters of a 0.1 molar sodium hydroxide solution to reach its equivalency point. So what is the concentration of the hydrochloric acid in moles per liter? Molarity moles per liter. One thing with titrations, so at the equivalency points, the moles of base equals the moles of acid. So what you could do for this problem is you could figure out the moles of base, and the moles of base then are going to be the moles of hydrochloric acid, and then divide by the volume. But you can also do it this way, doing the dimensional analysis. So we have 12.54 milliliters NaOH and liter NaOH to 1,000 milliliters NaOH. And we have 0.1 moles NaOH per liter NaOH. Then by the balanced chemical equation, 1 mole of HCl per mole sodium hydroxide. And the last step is the volume, 0.01 liters. That's 10 milliliters is 0.01 liters. And if we do all this, we will get, by unit-wise, do you see they all cancel? We'll get mole HCl per liter. I guess it would be HCl. So, and that solution. So, because that, look at and that's the concentration right there. So, I remember doing this in the previous lecture. That's one thing about teaching something 2 hours apart. Oh, it's even right there. Already in my calculator. That's the answer, and then my final answer will be 0.125. Because of the 3 sig figs. Okay. All right, recap for this one. We're neutral. We're doing a titration to figure out how much hydrochloric acid is in this. We know a concentration of sodium hydroxide, and we know it takes 12.54. So what we do is by dimensional analysis, but what the dimensional analysis means, we figure out the moles of sodium hydroxide here. Oh, actually, no, here is moles of sodium hydroxide. 1-to-1 molar sodium hydroxide to hydrochloric acid there, and then divide by the volume. So we have the moles of HCl divided by the volume, and then we get the concentration. So, questions with how this works? I have an easier but trickier problem for you. How many milliliters of 1 molar sodium hydroxide are needed to neutralize 10 milliliters of 1 molar H2SO4, sulfuric acid? There's a trick here. How many it's A? 5 milliliters. Same concentration, so it's going to be the. So how many B? 10. How many C? 20. How many D? 40. Okay, we got some people going for 10. So the equation here is going to be 2 NaOH plus H2SO4 makes 2 waters plus. Because of that 2 hydrogens and H2SO4. So are we going to need half as much or twice as much sodium hydroxide? Say 1 to 2 molar ratio. So every 1 mole of sulfuric acid, H2SO4, how many moles of sodium hydroxide do we need? 2. Are you specified? It's 2. So how many milliliters do we, so the same concentration, how many milliliters are we going to need? The same or double? Double. You following my logic there? Okay. All right. Any questions so far? Next topic. Yay. Gas evolution reactions. So this is actually how they execute people in gas chambers. So that's one of the ways, one of the approved ways to kill someone in the United States is to put them in a gas chamber. And the gas chamber reaction is here. It's hydrochloric acid plus sodium cyanide makes sodium chloride salt and hydrogen cyanide gas. And I've smelled cyanide gas before, and I can tell you, it smells great. It smells like roasted almonds. It smells really, really good. And I had for one of my classes, when I was a student, I had the curse of the terrible lab partner, if you've ever had that. And my lab partner, I was in lab, and it was organic chemistry lab, and suddenly I smell roasted almonds, and then the smell disappeared, and I was a little worried. Like, whoa! And I turned to my partner and what did you do? Partner said, oh, I mixed these 2 solutions together. It was acetic acid and sodium cyanide. And so I held my breath and left and talked to the instructor, and I'm like, we just released some cyanide. They're like, nah, you're fine. And the nice thing about cyanide that I realized, I looked up later, if you can stand and walk away from cyanide, you're probably fine. So cyanide poisoning happens fast. So it's the point of no return is really, really fast. So, and also the amounts that they were doing with wasn't that big a deal. Although the smell of it, we as humans, we get used to smells very quickly. It's a change of smell that we don't get used to. So, I can't smell the classroom right now, but sometimes when I come in here, it's kind of a slightly musty smell. It's not too bad. It's a newer building-ish, right? But there's a certain smell, like when you go in the building, it's a new smell, but I can't smell it. Like even I'm thinking about it, I can't smell it, kind of thing. But the same thing with that with cyanide is that we get used to it really quickly, and you can like, oh, almonds, goes away. That's one of the issues that people have is that cyanide is released, but they're like, oh, I smell almonds. Oh, I don't smell it anymore. I must be fine. 5 minutes later, dead. So, almonds, the flavor of almonds is actually cyanide. So when you eat almonds and you're tasting almonds, you're tasting cyanide. So if you are of the legal drinking age, and if you've ever consumed a beverage called amaretto, amaretto is made from almonds, but it doesn't taste like almonds. It's because all the cyanide has been removed in the distillation process. All the cyanide is left. And to me, it kind of tastes like cherries. So the cherry kind of flavor is amaretto to me, but it's an almond flavor. It's just that's what almonds would taste like without the cyanide. It would taste kind of like amaretto liqueur, but calmed down a little because it's, of course, amaretto is concentrated. So the danger for cyanide is if you smell it where it shouldn't be there. So if you're in a chemistry lab, if you're in a chemical factory and you smell roasted almonds, you shouldn't smell roasted almonds in a chemical factory. If you're at a Christmas market and someone has roasted nuts and you smell almonds, you are smelling cyanide, but you're smelling it from the nuts, and that's not enough to kill you. So the other thing is that I've noticed that when you smell the cyanide vapors, you get used to it really fast. Of course, the one time I did it, but I've read this is common. But when you have roasted nuts, the smell comes in different concentration gradients, so you continue to smell it. So it's that's one way that we'll notice smells if the concentration changes. So like if you put on like cologne or something like that, the concentration gradient of the cologne tapers off, so the change in concentration can actually you'll notice that. So they've looked at doing this with fragrances. They've like programmable fragrance diffusers that they stick out fragrance at different concentrations so that you don't get used to it. Like if you ever go into Abercrombie and Fitch, they have that fierce fragrance that they put out, and it's basically a big Glade plug-in. They stick it out, and then you're always smelling it. So there's ways they can do it. But anyways, cyanide, almonds and cyanide are the same flavor. So there's other gas evolution reactions. Sulfides. So you mix sulfides and acid. Hydrogen sulfide is released. And hydrogen sulfide smells like rotten eggs. It smells terrible. Really, really bad. And we haven't talked about oxidation states yet. We're going to talk about it next. Sulfur in the -2 stage. So we can smell sulfur down to the parts per trillion. We as humans, I mean. We as in humans. And there's this chemical here, CH3SH. This is methylthiol, CH3SH. They put that in natural gas. So you probably are familiar with the natural gas smell. Natural gas doesn't smell. There's no smell in natural gas. But we put something into it that we can detect down to the parts per trillion. Parts per trillion is really small. So parts per trillion, and because of that, and we pick something that we can smell very easily, and we don't like it. So toluene, I mentioned toluene, trinitotoluene. They sometimes use toluene in model cements. So you ever made a model and you have that, like you ever smelled that cement, the glue? It smells really good, right? That's toluene. You're smelling toluene from that. And you're like, oh man, give me that, I'm gonna smell it some more. So we put something that we can smell in really low concentration and that we don't like. You're like, ooh, natural gas, I'm gonna hang out here, it smells great. So natural gas and strawberries, two of my favorite scents, right? No. We hate sulfur smell. It smells bad. So we go away from it. H2S, so hydrogen sulfide, we're doing research right now because it seems that in large doses it can cause hibernation effects in humans. We're looking at it for space travel. So the idea is we take an astronaut and then hit the astronaut with a high dose of hydrogen sulfide, and then we can put the astronaut into a hibernation state and then can wake the astronaut up when we get to Mars, rather than have the astronaut endure the 1.5-year journey. So it seems to work best with kids. So children seem to be more receptive than adults. So, but it's trying to figure out. It's pretty hard to do this type of research though, because high probability you're going to kill the patient, right? So we're being very careful with this. Okay, so other things, carbonates and bicarbonates. So the word bi, you see you have bicarbonates and bisulfates. Bi in chemistry class means an extra hydrogen. So carbonate is CO3 minus 2. Bicarbonate is HCO3 minus 1. And so bi just means hydrogen. And carbonates and bicarbonates reacting with acid, it makes carbon dioxide and water. So that's your old school baking soda, vinegar, volcano reaction, the bubbling of CO2. Same thing with sulfites and bisulfites, makes SO2 gas. Gives me a headache whenever I smell that stuff. And ammonia, so if you mix ammonia, ammonium ions and bases forms ammonia vapors. And ammonia, it's weird. If you're awake and you smell ammonia, it can knock you out. And if you're unconscious and you smell ammonia, it can revive you. So smelling salts, have you ever heard of that before? That's ammonium carbonate. So you can put smelling salts next to someone who's been knocked unconscious, and sometimes it'll revive the person. Depends on how far gone the person is. But if you've ever smelled ammonia, it's a full body shudder. Let's just put it that way. It's a pretty strong, violent reaction. I've never been knocked out from it, but boy, does it give you a big jerk wake-up call. Okay, so but I don't have any examples with this because we've already gone through precipitation reactions and a little bit more in acid and base. This is kind of the same thing, types of reactions. Does anybody have any questions with this? Okay. Changing topics. This is the last topic, mind you. We're on our final topic for the chapter. So oxidation and reduction. So oxidation and reduction. And what we're going to get to, we're going to talk about oxidation states. And oxidation states are just a way to keep track of where electrons are. So later on, we'll learn that electrons are kind of this fuzzy sort of particle that's in many different places at once. And we're in oxidation states, you pretend that's not true and say that one atom has all the electrons. Okay, so oxidation, the most general term for oxidation is adding, so oxidation, there's 3 definitions. First one is plus O, plus oxygen. So iron, you can take iron metal and you can oxidize it to iron oxide. Also, removal of hydrogen, minus hydrogen. So this is more for organic chemistry. You can take ethylene, C2H4, you can oxidize it by removing hydrogen to form C2H2 ethyne or acetylene. So that's oxidation. The most general term for oxidation is loss of electrons, so minus E, minus electrons. So, and so these are all true, so oxygen, so I said iron oxidizes. What happens is iron metal is losing electrons to oxygen, and when it rusts. And when you rip electrons off of carbon in organic chemical reactions, hydrogen is said to be electron rich. So you're taking electron density away from the carbon. And then same thing and then there's general losing of electrons. So when we talk about reduction, if something loses electrons, the electrons have to go somewhere. So then reduction, the most general way to say reduction is gaining of electrons. So if someone loses electrons, something gains electrons. And so whenever oxidation happens, reduction happens as well. So whenever oxygen is added, something loses oxygen. So for iron oxide rusting and oxygen, or I'm sorry, iron rusting to form iron oxide, the oxygen gas itself loses oxygen. So if you're wondering where the loss of oxygen comes from. Also for reduction, you can take ethylene. So you can take ethylene, you can react it with hydrogen over something like platinum to form ethane. So C2H4 to form C2H6, adding 2 hydrogens. That's reduction. And in general, reduction is just adding electrons. So we talked about making metals. I said it's by carbon reduction. So you can take iron oxide or iron +3 +2, add electrons from carbon to form iron metal. So the iron is accepting electrons. That's reduction. So, and since oxidation and reduction will always happen together, we can say that they can happen together by redox. So redox means oxidation reduction. So it's just the first 3 letters of reduction, the first 2 letters of oxidation. Why redox? Because if you do ox red, you think of an ox painted red. So redox sounds a little more intelligent, I guess. Man, are you guys okay? You guys look like you're getting kind of bored. Sorry, are you just tired? The noon class is more energy. But it's not nothing to do, you guys. I think it's just because it's 3 p.m. Hopefully you are slightly entertained. We're almost at the end. So I'm going to stop the class. We're not going to go faster than the other class, so I'm going to keep them in parallel. And you'll probably get out of here at least 10 minutes early, maybe 15. Okay, so, all right, and now we're going to learn how to assign oxidation states. And these rules are hierarchical, which means rule number 1 is more important than rule number 2, more important than rule number 3, and so on. Oop, jeez. Sorry. I don't know why I went to Prime Video. Now you know I was watching Ancient Aliens. I love that show. It's so stupid. Aliens. Yeah. It's just, I think it's funny. Anyways. So, rule number 1, oxidation state of a free element is 0. So, rule number 2, oxidation state of a monatomic ion is equal to its charge. Number 3, and I'll go over an example of all these rules. The sum of oxidation states for a neutral molecule or formula unit is 0. For an ion, it's equal to its charge. Then in compounds, group 1A alkali metals always have an oxidation of +1. Group 2A, so alkaline earth, are +2. And rule number 5 is a chart. So fluorine tends to be -1, hydrogen tends to be +1, oxygen tends to be -2. Group 7A, halogens tend to be -1. Group 6A, oxygen family tends to be -2. Group 5A, nitrogen family tends to be -3. But it's about hierarchy as well. So fluorine being -1 is more important than hydrogen being +1. All right, so let's apply these rules here. So, and I'm going to make this smaller. Start off with chlorine, Cl2. So chlorine is a free element. That's rule number 1. Chlorine's oxidation state is 0. So, because it's an element, there's only one element there, one atom, one type of atom, I should say. And even though there's 2, chlorine is a free element. It's 0. It doesn't matter like ozone, O3, it's still 0. So, all right. Now next one, sodium plus. So it's a monatomic ion. Its oxidation number is +1, equal to the charge. Good? All right, potassium fluoride. So this is rule number 3. The sum of them, potassium plus oxidation of fluorine equals 0. That's a neutral unit. That's 0. And also, rule number 4, alkalis are +1. So that means that potassium is +1. So let's go ahead and put +1 for potassium. Plus fluorines equals 0. Fluorine is equal to -1. So fluorine is -1 there. Not very surprising. CO2. So carbon plus oxygen, 2 oxygens equals 0. So let me change different color. So you know that that's oxygen, not a 0, because my O's and zeros are basically the same thing. And if you look at the chart, oxygen tends to be -2. So carbon plus 2 times -2 equals 0. So carbon plus a -4 equals 0. Carbon equals 4. So 4 and -2, like that. Making sense? Next one, sulfate. So sulfur plus 4 oxygens equals -2. And why is this different? So carbon dioxide here, it's a neutral unit. It's 0. The charge here is where the -2 comes from. Okay, and then oxygen tends to be -2. Sulfur plus -8 is -2. -2. Sulfur equals 6. So we have +6 and -2. Questions with that one? Oh, no. There's no questions, or that you don't get it? What? You gave me is that a no questions, or is that a, okay, all right. I just wanted to make sure you're trying to read your body language. All right, potassium oxide. So 2 times potassium plus 2 times oxygen equals 0. Let me put the new color for oxygen there. So, and when I said the rules are hierarchical, so goes 1's more important than 2, important 3, 4. So 4 having alkali metals being +1 is more important than oxygen being -2. So for this one here, we're going to say 2 times +1 plus 2 times oxygens equals 0. So that means then 2 plus 2 oxygen is that, and you can see oxygen, doing the math, is going to equal to -1. Right, so we have +1 and -1. You're like, wait a second. Oxygen tends to be, oh, whoops, I didn't put this 2. Sorry. This is +1 and this is -1. You're like, wait a second, oxygen tends to be -2. Why is oxygen suddenly -1? Oxygen can be -1. And when it is, we give it a certain name. We call them peroxides. So if you've ever heard of hydrogen peroxide, it means that oxygen is in the -1 state. So there can also be fractional oxidation numbers. And if oxygen is in the -1/2 state, that's known as a superoxide. So peroxides and superoxides tend to be extremely reactive and actually oftentimes explosive. So if, for instance, you can take hydrogen peroxide and put it on metal, and it can catch on fire. So don't do that at home. So this is a problem with hair. So for hair chemistry, some people use metallic dyes. So if you've heard of the Grecian formula, that's lead acetate. It turns hair black. And if someone puts the Grecian formula on their hair and then goes and gets their hair colored, and if peroxide is used, people's hair can catch on fire. Not only that, peroxides they, like I said, they tend to be explosive, and they're impact explosive as well. So, I mean, you think of explosives, you think of things like dynamite. That's not impact explosive, but nitroglycerin is, but dynamite is not. That we talked about before. But some things are just so explosive, you tap them and they explode. Some things that we like to be explosive, airbags, they're impact explosive. But that's a good thing. That's how they're supposed to work. But most of the time they can be bad. Okay, so wow, we're done fast. So we're in the interest of keeping with the noon class. I'm going to end here. Sorry if I was boring you guys. You're just low energy.
Yep. It's a long day.
Long day.